angular diameter distances. I am from UFES, PPG Cosmo, right? So first I'll give an overall review of what's the status of the research on the effects of cosmological constant on gravitational lensing. I'll then explain a little bit about what model I'm using, why I'm using the metric that I'm using, and how I define the bending angle and how that's important for taking into account properly the effects of cosmological constant. I'll show how I'll test these corrections arising from the cosmological constant on gravitational lensing, and I'll give you some concluding remarks to finish the talk. So the main question that I'm trying to understand here is, do lambda affect the bending angle in gravitational lensing? Because when you observe the lensing effect, you already take into account the effect of lambda inside the angular diameter distances when you calculate the bending angle. So the lens map is something like this, right? And you already have inside here the scale factor, which when you calculate for a Robertson-Walker metric with cosmological constant, you take right into account here. However, maybe we're not modeling it right because we're not taking into account that our lens is immersed in an expanding universe with cosmological constant, and there are maybe metrics which are more proper to deal with this effect, the effect of, for instance, a point-like object or a black hole or another type of object immersed in an expanding universe. And so maybe there should be an effect there that not only comes from angular diameter distance calculated here, but also intrinsically from the bending angle. The first person to talk about this, more or less, was Islam in 1986, and he claimed that lambda should not affect gravitational lensing because, well, it does not appear in the geodesic equations of no rays, right? When you write everything for even when you write the gravitational lensing and the ray equation for the metric, for the Schwarzschild de Sitter metric, which already includes the effect of lambda inside the Schwarzschild metric, there shouldn't appear, right, an effect in the lens equation. But, however, Rindler and Dishak mentioned that there's an issue with how Islam proceeded, which is that he didn't take into account that you can't define bending angles in Schwarzschild de Sitter as you can in Robertson-Walker and in Schwarzschild, mainly because Schwarzschild de Sitter is not asymptotically flat, right? So the direction, the asymptotic direction which you're measuring your bending angle is not well defined as it is in Robertson-Walker metrics or perturbative Robertson-Walker metrics or Schwarzschild metrics. So they say, yes, actually lambda does affect the bending angle, not only through the angular diameter distances, but you need to define the bending angle properly. And they derived a correction, which I'll soon show you. However, their analysis was not thoroughly complete, was not thoroughly studied, and some people have taken it into account because they have not properly taken into account the effects of the observer when measuring the bending angle. Because in the end, you still have to take into account the Hubble flow because we're not static observers when we're observing gravitational lens effect. We're actually co-moving with the Hubble flow. So the fact is we also need to take into account the Hubble flow, right? Which I'll soon show you. And also the paradigm was a little bit shift from using purely a Schwarzschild metric to calculate the bending angle through a Map Vitimetric or in mailing Schwarzschild de Sitter metric to model it, right? And calculate the probable effects that should arise from this correction. However, the thing is, you see the correction derived by Rindler and Dishak shows that the correction should be negative. That is, you have an effect of the cosmological constant kind of debending the lensed object, the lensed image, because usually bending, usually gravity, of course, focuses the image of the lens, of the source object. And actually, lambda does the opposite effect, right? However, as I was mentioning, there were some rebuttals to the first paper of Hindley Ishak, which mentioned that they did not take properly into account the role of the observer, which is a comoving observer. So, in 2016, Piatella took the most general metric, which takes into account a compact object, and also an arbitrary scale factor, which is the Map Vitimetric, right? And in it, you can properly define the mass, which you have to define, which is the mass that of the lensing object, and also the way that the universe is expanding, right? And this already makes it a proper way to define the role of the observer, because you can, in this metric, properly change the frame in which you're measuring the expansion of the universe, and also observing the lens effect, right? So the current status is when you take into account the Hubble flow, right, and you define the mass of the object properly, there is a subdominant correction at next to leading order, right? The correction is really small. I forgot to add the dimensions here, but it's of the order of arcs, right? So this is sub-arc seconds, which the order of the correction. However, it is interesting because the correction is sensitive to different equation of states for dark energy, right? You can predict different effects, different corrections to the bending angle, which depend on the equation of state of the dark energy model you're using. However, the thing which I studied here is all these works, they were assuming, even the in the Mach Vit derivation, which is the most general one, that we have a constant Hubble factor in the model that we're using. That means that mainly our universe is de Sitter, right? So it's a lens immersed in the de Sitter universe. And the fact is, we already have detected lenses that are way farther than 0.7, more or less, redshift of 0.7, which is more or less the transition redshift from matter-dominated universe to lambda-dominated universe. And the thing is, we're modeling, if we want to measure, if we want to correct for the effect of the lambda, of the cosmological constant on the bending angle, we have also to take into account the effect of the transition epoch from matter to lambda, right? Because this is where we're measuring our lenses. And as I was saying, so for non-constant age, right, for models that go beyond the Sitter, we should see effects that are beyond the Bernoulli-dominated lambda. And the thing is, how can we predict these effects, right? And are they significant? Are they of the same order of the small lambda correction that we find when we take everything into account? And that's the question I'm trying to answer. Okay, so this is a really short summary of the Map Vitimetric. It has the nice features that for small mass parameters, it's more or less like a perturbed Robertson-Walker metric. For no mass parameter, it is the Robertson-Walker metric, right? And for no scale factor, it's more or less the Schwarzschild metric. Sorry, for a constant scale factor. Mu is defined as a kind of comoving mass, right? Because it's the mass of the lens object rationed by the scale factor. So so you see it's taken into account that the universe, as it expands, it already has a different place. Where the lensing happens is changing, right? So one way to better understand what happens is defining the Misner-Chapelle-Hernandez mass, which takes into account the areal radius, right? The mass that's enclosed in a space like hypersurfaces around the mass that you're trying to study. And okay, I'm going to choose this metric to model my effect. However, far from the lens object, that means far from where the lensing is happening, I'm trying to get an analytic form for the angular diameter distances in matter and lambda-dominated universes. So this is an expression which is analytic. This is not Taylor expansion, right? This is an exact function. Actually, this is just a series expansion of the hypergeometric function, which is not pretty, but it is analytic. I'm not doing any approximations here. So we can truncate it, and since it's convergent, it's perfectly analytic. I can go to an arbitrary order, and I know that the effects will stay to that order, right? So this is where what I will be using as my angular diameter distance, which will, of course, appear when I'm trying to calculate the full bending angle. And, okay. So this is the lens configuration, right? My angular diameter distance is given by that expression that I showed previously. I'll define characteristic scales, which will facilitate a lot when integrating the bending angle, which I'll soon define. And the main idea is that here we have a Map Vitimetric effect, right? That mu mass parameter which I was showing you will be taken into account here. So that mu will be an expansion parameter, which will soon be related to alpha, which is the first order solution to the bending equation. And otherwise, elsewhere, right? I'll take into account that this distance is given by the purely Walker solved by the matter plus lambda content, which I showed you in the previous slide. Okay? So the thing is, you can have an approximation, since I'm assuming that my lens is more or less, this angle here, this YS, is small enough so I can approximate the tangent here by the relation YS XS, right? And when I do this approximation, I can obtain expression 4, which gives the tangent to the ray, the null ray which I'm following, right? And the solution to this equation, I'll define as the bending angle, right, in my cosmology, in my model. So this should be the full expression. And the thing that's nice there is that it has an analytic solution. But I'm doing a series of approximations, well-motivated approximations, right, to tangent that I just told you. And the thing is, before I can perform the full integration, since you have this distance, this YS, really small in this relation, I'll assume that Y here in this equation is the first order solution to the lensing equation, which means it's just a straight line, right? Of course. We should find a straight line if you're integrating the tangent here and you have a first order solution. So equation 4 is the equation I'm trying to solve, and it's taking into account all the things that I'm trying to include in my bending angle model, right? So lambda, matter, and the effect of the Map Vitimetric. And the expansion parameter, of course, is alpha, since I'm including here the alpha to first order solution, okay? And this definition is not trivial. You can maybe talk to me a little bit about it later. But it's a definition that how can I say? It's not the same as the one in the usual lens approximation, right? But the thing is, you have to define an angle like this whenever you take into account metrics that are not purely Robertson-Walker, angular diameter distance, plus an object model after Schwarzschild. The thing is, it's not a pretty equation. What I'm doing here is I'm expanding x, right, as the angular diameter distance that I previously defined through that ugly series. However, as I said, everything is pretty analytic. You could integrate, if you would like, this to the nth order. However, I chose to stop at third order, since I'm trying to understand if the corrections are of the same, have the same effect as the already small corrections arising from the first order correction arising from lambda. And this expression 5 is giving me the full lambda plus matter plus the first order plus the 0th order correction to the bending angle. So I can integrate this. It's analytic, the integral. It can be written in terms of elementary functions. It's not pretty, so I'm not going to show you, but I can, if you want me, I can send you the paper. And this graphic showing the red line, the correction including all the terms, that is the third order correction, right, the delta 3, which I'll define. And the blue line is the first order correction, right, if we had taken just 1 plus x here, okay, which is the first order correction to the usual Schwarzschild bending angle. And the thing is, this graphic doesn't tell us very much, but the thing, you have a small correction, right, to the correction already arising from lambda. However, in this graphic, you can see that there is the effect of the higher order corrections arising from the lambda plus matter transition age when you're integrating on the redshift. They are of the same order of the pure lambda correction, right? So there is an effect of the same order when you take into account lambda plus matter cosmology instead of purely lambda cosmology. So you have an effect, so you have a correction of the same order. That is, it is important to take into account the transition redshift and the transition age when you're integrating over the alarm site. And especially when you have more or less ZS over ZL going to 1, that is, we have how the closer we get the source to the lens, the higher this correction is. However, this is of course not what we observe usually. And even if it would be singular, the behavior here, we will never observe something like this. I mean, even if we should model something like this, for instance, inside our galaxy, it wouldn't be in the regime of strong lensing. So none of this would be valid. And the question is, okay, you found a correction that comes from the lambda plus matter phase, arriving from the line of sight integral. Can you, for reals now, check if everything that you've done is significant? Can you compare this with observations? And the thing is, that's what I'm trying to do. And what I'm doing is I'm selecting some Einstein rings systems, right, which are super idealized. I'm using visual inspection because I'm trying to get the most perfect rings that I can see, which allow me to use a Schwarzschild lens model. And the thing is, I'll try to get a mass prediction, right? A mass prediction from the system using all these full corrections. The 0th order, which is just the Schwarzschild lens mass estimate. The first order, which was obtained in Piatella's work. Right. And the third order, which is the correction found. Sorry. And the third order correction in this paper, right? And I'm still doing the minimization, but I can already see that, no, we shouldn't really take into account all of this if we want to model gravitational lenses in the strong regime. This is more or less what I'm trying to select. I already have a reduced set of 20 Einstein rings. I'm taking mainly from the Castle's Nest DSS for surveys, all right? And the remarks is that all of these systems have systematic errors, right? And the mass estimates are really complicated because you have to assume a mass profile already. There are no Einstein ring, no perfect Einstein ring systems, such as there are no perfect Schwarzschild lenses. And the order of the correction is still really, really small, okay? To beyond first order. So in conclusion, there's mainly not only a dependence on lambda, but also on the full cosmology, right? The correction is of the same order as the lambda correction. However, it is really small, right? We cannot measure it so far. And the usual weak lensing approximation, the usual bending angle expression and lens map approximation with Schwarzschild lenses is completely valid so far. So that's what I've obtained, and thank you so much for your attention.
Very good. Thank you. Questions?
So you are working on a space-time that is not asymptotically flat, right?
Yes, exactly.
So you cannot use the straight line as a standard curve from which you will measure your deviation, right? That's the problem.
Yes, because usually when you're doing naive strong lensing, the thing is you assume that since you're on Roberts-Walker, you can just say that the directions are given by the asymptotics from the angular diameter distances, right? And since Roberts-Walker is conformally flat, this is just rescaled by the scale factor. And however, when you don't have a metric that is conformally flat, you can't define the lensing angle, the direction which you're measuring your angle from in the usual way. So you have to define it.
I didn't understand, how do you deal with this problem? What is the definition that you use?
The definition that I use?
Yeah.
What I do now is that I integrate along the node geodesics of the metric here. So this is the geodesic equation, more or less, the node geodesic equation. What I'm doing, I'm integrating over it. Of course, I'm doing some approximation so that I can model my lens system better. More or less, that's what it is. However, this is not a trivial thing. That's what because I can talk to you about later, but it's not trivial to define bending angles in arbitrary geometries. You have to understand the no rays of your space-time. And this is just an approximation that allows us to obtain a bunch of analytic, really nice expressions, more or less.
Okay, thank you.
So Map Vit is basically FRW with inside the Schwarzschild, right?
More or less.
So if you're far from the mass, can you recover the usual lensing formalisms, like with lensing potential?
No, not. Tá, tranquilo. Not really, because it becomes a perturbed Roberts-Walker metric, right? And it would be something like lensing with the Newtonian potentials, if you call them the same as the mass parameters, right? It becomes more or less Roberts-Walker with in the perturbed Roberts-Walker in Newtonian gauge, which is well understood, at least as far as gravitational lensing goes. However, it is not conformally flat. You can't make this metric conformally flat unless you take the mass parameter to be constant. No, you can't have a mass parameter because this violates this generates a non-null Weyl tensor.
So we thank Pedro again.
Negócio enrolado.